this term times this term, p times y0 squared, and this one times this one minus that one. So you end up with equation, second order equation with one unknown. T is unknown. Okay? And you can simplify this equation. Becomes p squared this is a second order equation with one unknown. You solve this equation, you get two values for p. So we're trying to determine what is the minimum loading for this column to have buckling. That means we should choose that smaller one. Right? You are going to get two values for p. So the minimum is 1.68 into 5 Newton. This is the loading you get through this procedure. So this is the buckling loading you will have. Maybe not, because you need to do one more step. You need to check this number is smaller or larger than the py, pz, or p alpha or not. Because you calculated some loading along y direction, z direction, twist angle direction already. So if your calculated loading is larger than one of these three values, maybe the minimum loading should be one of these three. See what I mean? If your calculated P is larger than one of them, Py, Pz, and P alpha, that means your loading cannot achieve that P you calculated. The buckling will already happen due to some P alpha, Py, Pz, or P alpha. But right now you have one number for P. You calculate, you compare that number, 1.68, and compare with Py, Pz, and P alpha is smaller than one of the three. Smaller than one of the three. That means your calculated P is a minimum loading for buckling to happen. Okay? But if P is larger, suppose this one is 1 10 to 5th order Newton. So if P is smaller, is larger than this one will be the buckling loading. Okay? So minimum loading will be the buckling loading to have. You have four values for P actually. After the calculation, you will have four values: Py, Pz, P alpha, and the P you calculated from that equation. So you should choose the minimum value of these three different numbers, four different numbers. Okay. So this is the next step. And follow this example, you can do that one in your homework, because I just changed the geometry of the cross section. All of the procedures will be the same. You just calculate the determinants of that matrix. And in homework, you also have buckling of plates, but that one has nothing to do with hand calculation. I want to introduce a little bit about hand calculated buckling of plates. Because hand calculation of buckling of plates is very tedious. So I didn't assign any part about hand calculated buckling in plates. But we need to understand what is the procedure and what is the fundamental principle behind it. By the way, yesterday we have a visitor from the industry advisory council, right? A lady gave a lecture here, I remember, in this room. So actually, I met with them, and one of the guys from a large company. I don't know what is the name of that company, and I asked her what I'm supposed to teach the structure analysis engineer, and I asked him what I'm supposed to teach in my class, because I'm teaching structural analysis to make my students have a very smooth transition in their career if they want to pursue their career in structural analysis. He told me that teach them more about fundamental principles about structural analysis. Do not cover too much about how to use software. I asked why, because students prefer to be using software. Is that software can be trained maybe in 3 months training session, but fundamental principle can make them get promotion more easily. Because most people get promoted is because they understand what they are doing. They can be independent working on a project, but software user cannot be independent. Software user has to be guided by some people who is very good at it, fundamental principle behind the software. So that is his point. And he offered to give a lecture today, but I said my lecture time is 1 o'clock. His airplane ticket is 12, so he could not make it. So he offered to make a lecture to you guys. I was very happy yesterday, but he checked with me this morning and said he has to take off. So that's a pity. But he has 20 years experience in doing structure analysis. He graduated from our department with a bachelor degree and then got promoted on and on. But he told me that benefits of this education here is to understand more about the principle, not software. He learned to use SolidWorks, MATLAB, Core E when he was a student. But what he benefited, what he got promoted is because his theoretical foundation is better than some peers in his company. So this is the point that he asked me to share with you. Appreciate more about the equations. Okay? So this is why I'm introduced a little bit what is the equation for buckling of plates. In homework, you only need to do the answers part, but you need to understand what is the equation behind that problem. Okay? This is a plate. If you apply compressive loading along x direction and also y direction, and also shear force. Most of the software user in his company do not have a bachelor degree. They only have a certificate because they are very proficient in using software. They do not earn any degree, actually. This is what I was told. The senior people, usually they have a degree. This is the difference. I hope all of you guys can be manager, senior engineer, do not be just preliminary entry level. That is not good. Right? So this is the loading applied on the plate, and the dimension along this direction is A, dimension along this direction is B. And what is the Gauss equation for column buckling? Anybody still remember anything for the Gauss equation about buckling of column? The first order partial differential equation is this one. A square B second order equal to 0. K equal to P divided by BI. This is the setup. This is what we have learned from the very beginning about the topic of buckling. Okay, we are trying to determine what is the deflection along this direction in traffic. This is x direction, so this is W. That equation is used to solve for the deflection of this beam when buckling happens. Same thing. If I have a plate, we need a Gauss equation. That Gauss equation is pretty similar with this. I'm not going to derive it, but we'll look at that equation. You will see it's very similar with the Gauss equation for column. the three terms on the right, let's look at the three terms on the left. And if you compare this three terms with that two terms for column, you only have one additional term, this term. And this one, this is along x direction because this is two-dimensional analysis now. So you have one term for x along x direction, deflection about with respect to x fourth order. You also have buckling along y direction. So you have deflection with respect to y fourth order. And you have a cross term. That's why you only have x, because that case just one-dimensional analysis. This one for plate, actually it is a two-dimensional analysis. So you have cross terms, fourth order, and this is the three terms on the left. On the right is the loading. Nx, ny, and nxy is the loading along x direction, loading along y direction, and the shear force. So this one is a constant related with the shear modulus and Poisson's ratio. Just like K in column is related with modulus and the sectional property, in plate we also have something related with the modulus and sectional property. D for plate is E T Q 1 minus mu squared. This is constant. If the thickness, T is the thickness, E is the modulus, mu is the Poisson's ratio of the plate. And if we want to solve for the in buckling of columns, we solve for W. W equals A sine pi x, something like that. But if we want to solve for W for this equation, it's not that easy. We have to make some assumptions. You have a question about this?
What is the first two terms in the denominator?
Which one?
Rotation.
This one?
Yeah.
12.
Oh, okay.
12. Sorry. This is 12. Remember. Okay. And if we make some assumptions, we will assume the shape of the buckling mode. In the homework, I'm asking you to plot what is the first, second, and third order buckling mode. So you will see this shape, deformed shape, is following a sine wave shape or cosine wave shape. So that is from assumption, analytical assumption. We are assuming the deformed shape is following a function like this. Why we are assuming a function like this? Because we are dealing with, I should say, the boundary condition about this plate. Is all of the four edges are constrained by rollers or pinning. Okay, all of the edges of this plate are constrained by pinning joints. So that gives me some information about what is the deformed shape should be, because deformed shape should be at least satisfy the boundary condition. So if you have a deformed shape like this function will satisfy the boundary condition at least. And then you can substitute this deformed shape into this equation, solve for the unknown. This is the same procedure as what I have done in column. We assume the buckling shape is following a sine wave function, and then we solve for the coefficients. This is the same procedure. But it's more complicated because it's two-dimensional. One wave is along x direction, the other sine wave is along x direction. M and n are integers from 1, 2, until infinite. It depends which mode you are looking at. Okay, in ANSYS, in the last problem we are going to do in homework, ANSYS will plot first mode, second mode, and third mode until arbitrary mode you want to plot. And you will see what the deformed shape is following the sine shape, the cosine shape sometimes. So if we substitute this W into that governing equation, and we also assume nx equals to n, ny is 0, nxy is 0. That means we are dealing with a plate like this. We're dealing with a plate with a loading like this. Only a compressive loading along x direction. What is the deformed shape will be? And in this case, we substitute that W into that equation and simplify it. We will get this is summation from 1 to infinite number, and the first order this equation is just from substituting the function W into that common equation. Okay? And you end up with this equation. You don't have to know the detailed procedure because I'm not going to pass it. Okay? This is new. It's very tedious. You have many terms. Fourth order. Look at this common equation. You have fourth order about that W. So you have W is like this. You have to take first order, second order, until fourth order, and term by term. And then put them together, you can get this equation. Okay? So this is the procedure. And look at this equation. This is a coefficient. Forget about this summation. This is a coefficient. And this three terms, A times sine equal to 0. So this is a function in terms of x and y. This is an arbitrary number. Something times the arbitrary number equals 0. That means the coefficient has to be 0, right? Because this is an arbitrary number. It's a function of x and y. Some ax equals 0. X is arbitrary. The only condition is a has to be 0. So this is the philosophy behind it. And the coefficient is 0. That means in column buckling, we are solving for P. In plate buckling, we are solving for N. Right? N is the applied loading along x direction. This is the equation, one equation, one unknown. Unknown is N. So you can solve N. This is a critical loading for a plate to have buckling. When you look at this procedure, I didn't go through all of the detailed procedures, but the philosophy is the same. Apply loading, you have common equation, assume a deformed shape, and substitute that deformed shape into that common equation, coefficient is 0. This is the same for buckling loading. For buckling, assume a function, and then substitute that function into the common equation, coefficients should be 0. I got P. This one is the same, you get N. This is the critical loading for a plate to have buckling. N from 1 to 2 until infinity, N from 1 to 2 until infinity. So the critical loading, the minimum loading for the plate to have buckling is N equals to 1. Look at this form for N. It's a function of M and N. M and N are integers. So at least the minimum loading along x direction should be following N equals to 1. If N is larger than 1, That n value is larger than NCR. This one is critical loading.
So with the algebra, how did we get a square to the term in the critical loading?
Here. So my notes, maybe I dropped one term. I mean this equation here we should have a square. In my notes I do not. I need to double check. Otherwise, if we do not have a square, we will not have that square. So definitely we should have something like that. Because we are going to take the first derivative of this one, so we should have. I'm going to check this one. We should have a square here, and then if we have a square here, square is here, and then square will be here. So this is maybe I dropped one square here. I can check the textbook right now. Yes, we have a square. In textbook, we have a square there. So, I would encourage you guys to, if you have time, read something in textbook. If you did my homework, exam 1 and exam 2, if you read the textbook, you'll find some information that's related with the problem in homework in textbook. Okay? Exam 2, especially in exam 2, I just changed a little bit of problems in textbook and put it as an exam. So if somebody is reading the textbook, definitely will benefit from that reading. But it's not exactly the same. I will change something. Okay. So the minimum critical loading will be pi a b m squared n squared plus b squared, because n equals to 1. I can further simplify this. Becomes pi b squared times mb a plus a mb squared. So this is just simplification. From this to this, I just shuffle some terms. And then there's a concept related with this coefficient. We define this coefficient as k. So this becomes k times pi squared d divided by d squared. There's a name for this k. K is the buckling coefficient of the plate. Okay? This k is the buckling coefficient of the plate. Why it is so-called buckling coefficient of the plate? Look at the two terms. It's a ratio between b and a and b. That means this buckling coefficient is a function of the ratio between the width and height of that plate. So in homework, I'm asking you to model the plate with different ratio of the width between the width and height of that plate. 3 different cases in homework. We are going to do this in answers. You will see the shape will be different because the buckling coefficients will be different. Buckling coefficient is different because the ratio between the width and height is different. So you can check this after you finish your answers modeling. I'm going to stop talking about plate for buckling and put something else. I'm not going to too much details about how to do hand calculation in buckling. But something more useful is realistic engineering structure analysis. Buckling analysis using energy methods. That is more convenient than what I have done, but it's not that accurate. What I have learned in the previous 23 to 4 lectures is analytical methods. We assume, deform the shape, and solve that Gaussian equation to get Parkin law. This one is energy method. This one will be more convenient, but not that accurate. So what is the figure behind this? We come back to look at the column. This is x, and this is the deform the shape. And because you apply a compressed loading along this direction, the length of the column will be decreasing. I'm assuming the decreasing of the length is d theta. So for the energy method is we are going to construct the strain energy is a function of internal energy minus the work done. If you do not remember this formula, just go back to check the notes about the stiffness method. We derive the stiffness matrix using this function. We minimize this pi to get the stiffness matrix for bar and then for beam. This is the same thing. This is the same form. Strain energy and work done. Strain energy minus work done. This is energy principle. We're going to minimize this pi to derive what is the buckling load. So we need to deal with the first term first. dV. Right? This term, if you follow Hooke's law, this sigma is stress, epsilon is strength. dV is volume integration. Okay? We convert this strain into a stress. This becomes sigma squared 2E dV. And then what is sigma? In mechanics and materials, sigma equals to my divided by A. So use that, and this equation will becomes m squared y squared e I squared. dV becomes dA dx. X from 0 to air. Convert the volume equation to a length equation. Then this one, the area equation, we're converting the volume equation into a dA and dx. So this one becomes 0 L m squared 2E I squared y squared dA dx. We use this procedure many times actually. When we derive the stiffness, we follow the same procedure. This one is I, the area of the inertia of the cross section. So that will give you m squared 2EI dx. And then what is m? M is related with the second derivative of the deflection. So this EI, second order derivative. So this is m. If we use m in this one, we get 0 L EI T E omega dx. So this is the first term. After here, we finish the derivation of the first term in pi. This is pi. We have two terms. I derived the first term. Why I'm deriving this? Because I need to write the function in terms of the Wx. W is the deflection. I'm trying to solve for that deflection. You apply a compressor loading. I'm trying to solve for W. Right? I need to write everything in terms of W. So the first term, strain energy, is in terms of W. So what about second term? second term is P delta dV. P is the loading. dV is just integration, volume integration. So we need to figure out what is this one. What is the relation between this one and the deflection? dW is the decrease of the length of the column along the longitudinal direction. W is the deflection along vertical direction. What is the relation between d delta and W? So you need to check the geometry of the column. This is the original column. After you apply a loading, to deform the shape, probably it will be like this, upwards or downwards. Both of them are possible. So this is the deformed shape. And one small segment here is ds. If I'm going to take the ds out from the deformed shape, ds is this much, and this is original x, this is dx, right? This quantity is delta. The baseline is the anti-deformed shape, and ds is the deformed shape. I take this segment out from the deformed column, and this is anti-deformed shape still there. This is original length, ds. This is d delta, decrease along the length direction. So we need to do some geometry calculation. This is the rotation theta, right? Because this is the deformed shape. This is the deformed shape. So this one is the rotation theta. And I'm trying to figure out what is the relation between ds and ds. Look at this triangle. ds should be dx squared plus the height squared plus that one, maybe I need a notation dl squared. dl is the height of that small triangle. This is theta because the plane is not fine enough. This is theta. This is the rotation from anti-deformed shape to deformed shape. The height is I loaded as a dl. So if you look at the triangle, is ds equal to that much. Because theta angle is quite small, dl is equal to ds times theta. Theta angle rotation is very small, just like the rotation. This is arc length. This is the radius. So the relation between dl and dx could be arc length. Radius times the theta is the arc length. Okay, dl equals to dx times theta. And so this one will be, if I use this equation, it is square root dx squared plus dx squared theta squared. Right? So this one becomes dx times 1 plus theta squared. This is ds. And then what is d delta? Because this is the term we are trying to figure out. So d delta equals to ds minus ds. The change of the length. ds is the length of the deformed column. dx is the length of the undeformed column. The physical meaning of d delta is the length change. So deformed shape, deformed length minus undeformed length. You get the length change. Okay? And then you can use, because if you grab something for ds already, dx 1 plus theta squared minus dx. This is d delta. We still didn't get what is the relation between d delta and w yet, but we are almost there, because theta is the rotation of the column. Rotation is related with the first derivative of the deflection. Okay? So if you use theta is equal to dw dx. If you do this equation, this one can be simplified dx 1 plus dw dx squared minus dx. I convert the rotation to a term. related with the first derivative with deflection. Up to here is still very complicated. D delta, this one, we need to have a simplified term. Otherwise, we cannot use that part. So we can do a Taylor expansion. This term, square root of something, you can do a Taylor expansion. It's equal to dx. If you do a Taylor expansion, this one is dx square plus some high order terms minus dx. From here to here, I did a Taylor expansion about the square root of the two terms. Okay? How to do that? You can check even in Wikipedia, in Wiki, you can see what is how to do the Taylor expansion of this. 1 plus x square root of this one. There's a formula for this. If you do a Taylor expansion, you can get this. This dx, this x is just replace that x with d omega dx. You can get this. So look at this. Dx times 1 plus something. I drop the high order terms because high order term is very small. D omega dx, dw dx is already very small. The rotation is already very small. The high order terms is dropped. And then this one will be cancelled with this one. We only have this term. This is d delta. So up to here, we finish the second term. And then we combine the first term and the second term. What do we get? For pi. Because I derived the first term and second term already, so the pi will be ei d delta is this one. This is the energy. This is the total energy. Strain energy minus the work done. This is the total energy for that column. When you apply a compressive loading, we will have a compressive loading, you will have deflection W. So this functional form, this energy is in terms of W only now. Right? Only unknown. All of the other things are known. Young's modulus, sectional property, driven loading, the only unknown is W. So according to energy principle, this structure is in equilibrium, the energy has to be minimized. The same principle, we follow the same principle to derive the stiffness matrix. Okay? So this pi has to be minimized. And then we come back to solve for this. Next time I'm going to continue. I still have 5 minutes, right? So I'm going to finish this. Okay?
Yeah, 1 minute.
1 minute? Okay, I'm going to stop here. So my watch, only 5 minutes.